All right. So thank you everyone for joining back to this afternoon part of the workshop. We're starting with a talk by Joe Tasseroti, an invited talk by Joe Tasseroti. Joe has done very interesting work recently, including some very interesting works on verification of concurrent and distributed systems, and he's going to tell us about that. Joe, please.
Yes, thanks for the introduction. So today I'm excited to talk to you about our work that we've been pursuing over the past couple of years, developing program logics for reasoning about systems that are concurrent and crash safe. And this is a joint work with a bunch of colleagues at MIT. So to give some background, the kind of systems we're interested in here are storage systems that make guarantees about the persistence or durability of data that they manage. In particular, these systems promise to keep your data intact even if the system were to crash. So I'm thinking of things like file systems, databases, various key value stores, and so on. And when I'm talking about crashes here, I mean externally generated events, things like power being pulled or a process being abruptly terminated, and so on. So generally, if such a crash occurs, the system will need to run a recovery procedure after restarting in order to restore various system invariants and bring things back to a good state. One subtlety here is that a crash can happen again during recovery, right? So you could lose power yet again. And we want the system to be robust even if a crash happens during recovery itself. All right, so to be more specific, I'm going to use a running example to motivate some of the challenges here. And this running example is going to be a simple disk replication library. So the idea here is we'll have two disks, and the library will issue write and read calls to it. And what it'll do is mirror our writes across the two disks, and then reads can be serviced by reading from whatever disk if it's faster to read from one or the other. All right. So we want this to be concurrent, so threads should be able to access this in a multi-threaded context. How would we implement such a thing? Well, to achieve thread safety, what we can do is provide a lock for each address on the disks. Okay, so our write procedure then is going to acquire the lock for the address A that we're trying to write to. And what it's going to do is mark a bit on disk indicating that we're about to pursue a write to this address A. All right, once that bitmap bit has been marked, we can go ahead and write the value to each of the two disks. When we're done, we clean up that bitmap address, and then we can unlock the address so that other threads can see the write. Now, if a crash occurs between lines 4 and 5, then the disks will be out of sync because we'll have completed the write to disk 1, but not yet written the value to disk 2. Okay. And of course, because this is a multi-threaded library, there could be many threads that were in the middle of writes to different addresses. Right? So after a crash, many addresses may be out of sync. So our recovery procedure that we're going to run when we restart will bring the disks back into sync so that we can resume normal execution and continue servicing writes and reads. How does recovery work? Well, what it does is it loads that bitmap that we were maintaining that was keeping track of which addresses were possibly in the middle of a write. And then for each of those addresses, what we're going to go do is copy the value from disk 1 over to disk 2. Okay, so we can think of the write on line 5 as completing or wrapping up a potentially interrupted write that was going on when the system crashed. Now, a key invariant that makes this all work is the fact that during our write procedure, before we actually modified the values for the address on disk, we made sure to mark that we were about to initiate a write in our bitmap. Okay, and that's very important because our recovery procedure is only going to do a copy for things that were marked as dirty. All right, if we didn't maintain this bitmap, our recovery procedure would have to pessimistically assume that potentially every address would be out of sync and have to copy over the whole disk, which would be very slow if we had a gigantic disk. Okay, so very critical that we maintain this invariant of always marking dirty before actually carrying out a write. Now, in this little simplified presentation of the system, it seems easy enough to get that right. But as I was preparing this talk, I was refreshing my memory on how the corresponding code works in the Linux kernel. And I was amused to see that the most recent commit was in fact fixing just such a bug where on a particular code path and configuration, the system would not update the bitmap before carrying out a write. And so that meant if the system crashed, recovery wouldn't actually bring the disks back into sync. Okay, so, in actuality, these things are hard to get right and people make mistakes. So why, in fact, are these systems in general so difficult when we have this combination of concurrency and crash safety? Well, concurrency is by itself already difficult. We're all familiar with the fact that if you have, say, two threads running A and B, then we have to consider all the possible interleavings of operations by these threads. So here I'm just listing a few, but there are many more. When we add crashes into the mix, there's yet more non-determinism because for each possible interleaving, we have to consider a crash that could occur at any prefix of the interleaving. All right. And then on top of that, we said that crashes can repeatedly occur. We're not just considering one possible crash, but a crash can repeatedly occur after the system restarts. And so really we have to consider traces that involve sort of arbitrary extended repetitions of recovery with crashes intermingled. Okay, so basically we have this huge problem of all of the bad non-determinism of concurrency just gets worse. So what I want to talk to you about today is a program logic we've developed called Perennial for reasoning about these systems. And there's two key things that Perennial delivers on to make this kind of verification task simpler. The first is that we can reason about each thread separately. So we do thread local reasoning, and therefore we don't have this combinatorial explosion of different interleavings. And the second is what we can do is establish that a recovery procedure is idempotent, which means that we'll prove once and for all that it can tolerate repeated crashes. In terms of the implementation of this library, so it's built as an extension to the Iris concurrent separation logic framework. And so we inherit all of Iris's powerful mechanisms for reasoning about concurrency. In particular, we're able to leverage the very well-developed Coq mechanization of Iris to that end. And as a practical matter, it supports verifying Go code through a tool that one of my collaborators, Tage, has written called Goose, which he spoke about at CoqPL, I think 2 or 3 years ago now, which can import Go code into a representation that the program logic can reason about. Okay, so because Perennial builds on Iris and concurrent separation logic, and that's a key part of how we're going to get thread local reasoning, let me just recall some of the basic ideas behind concurrent separation logic and how it achieves thread local reasoning, and we'll see what changes need to be made to support crashes. All right, so this will be familiar to some people in the audience, but let's just make sure we're on the same page. So the key idea behind separation logic is the introduction of a new connective called separating conjunction, which we write as this asterisk symbol, which I'll pronounce as star. All right, and the interpretation of the formula P star Q is it says that, well, it holds in a given program state if we can split the program state into disjoint pieces, which satisfy P and Q respectively. Okay, so graphically, if we imagine on the left here an array of memory cells, we'll say that that satisfies P star Q if we can split them into disjoint chunks, one of which satisfies P and the other satisfying Q. So why is this idea of separating conjunction so powerful? Well, among other things, it enables thread local reasoning through the famous concurrent composition rule, which I'm showing the inference rule here on the left and illustrating it graphically on the right. So this says that if we want to reason about the concurrent execution of two threads, E1 and E2, which I'll write as E1 vertical bars E2, okay, then what it suffices to do is to show that our precondition can be split into two disjoint pieces, P1 star P2. And then what we do is we prove triples separately about each of E1 and E2, where as a precondition for E1, we assume P1, and a precondition for E2, we assume P2. And then what we get to say is that the post condition at the join point of where the two threads join together is Q1 star Q2, the separating conjunction of the post conditions of the two threads. So the reason, like the fundamental insight that Horn had in kind of giving the formulation of the rules, was that we can think of thread EI here as owning the resources described by PI, the thing in its precondition. So because E1 owns P1, we can kind of think of it, the other thread is not going to interfere with what it does, which is what licenses us to prove separate triples about each of the program, about each of the threads. So now, how does this story handle crashes? All right. Well, if we imagine that a crash occurs in the middle of execution of E1 and E2, then when we restart, we're going to run the recovery procedure, as we said. The key question we have to answer is, what does the recovery procedure ER own after the crash occurs, right? Our triples that we previously had proven about E1 and E2 really only said something about their post conditions, the state of the system after they finish running at the join point. So a crash by its very nature could occur in the middle of execution, and so we're not really equipped to say anything about the status of the system at that midpoint. All right, and so in Perennial, what we've done is shown that we can adapt mechanisms from separation logic for thinking about ownership to account for crashes. All right. And so basically, if you take any idea that someone has developed for concurrent separation logic and think about it through the lens of crashes, in my opinion, a very natural extension to those ideas that the wonderful concurrent separation logic community has developed. Okay, and what I hope to convince you of is that this is not just like a Girard style mustard watch of just tacking on crashes, but the introduction of crashes to these separation logic principles actually tells us something interesting about the way we should think about crash safety in these systems. All right, so I'm going to talk about a couple of those ideas that we've come up with. And the first that I'm going to tackle is how we can expose intermediate state of the system in a way that lets us recover the concurrent composition rule. And the mechanism we're going to use for that is a notion called a crash condition. Okay, so crash conditions actually occurred in an earlier program logic for sequential systems called crash Hoare logic. And the idea of a crash condition is we're going to take our Hoare triples and we're going to add a new assertion to get a Hoare quadruple. So here that assertion is T. And the idea is that this judgment will hold, it holds, meaning will require that the crash condition T has to hold at each intermediate step of E's execution. So the pre and post condition P and Q have their usual meaning, but we're making a further guarantee that at every intermediate point as E's take steps, T will also hold. All right. So let's see an example of such a Hoare quadruple. So if we introduce an assertion here, a points to assertion for describing the contents of disks, where we'll write A points to B, subscripted with a D, to say that disk address A contains block contents B, then a Hoare triple for writing to address A might say something like, well, if in the precondition the address contained contents B1 and rewrite B2, then in the post condition it will contain B2. We can make this into a quadruple where the crash condition is going to capture the fact that, for our purposes, a disk write of 4 kilobytes is going to be an atomic operation. So either the system, if we get interrupted by a crash, either it'll happen before the write has taken effect, in which case we'll be on the left side of this disjunct. And in that, so we'll say that the disk still contains contents B1 at that address, or it'll happen after the write took effect, in which case the address will contain B2. All right, so more generally, we can derive a quadruple from a triple when we're thinking about an atomic expression E. So what this proof rule says is if you want to derive a quadruple about E with crash condition T, then it suffices to show that the precondition P implies a crash condition. And you also have to prove a Hoare triple where in the post condition you have to show that T still holds. All right, so the leftmost premise is capturing the idea that the crash condition has to hold before E takes a step. And the triple post condition is capturing that T has to hold after you take a step. Okay, and this is very crucially here, I'm thinking about an atomic expression, so one that reduces to a value in a single step of execution. Okay, so from this rule, you can basically take all your kind of standard Hoare triples from the primitives of your language and derive a sensible quadruple for handling those. So the key difference in the way that Perennial treats crash conditions as compared to the sequential crash Hoare logic is that in Perennial, the crash conditions are thread local. They only describe the state of the system or the state of the resources controlled by a particular thread. All right, and that's important because it enables us to still get concurrent composition in the presence of crashes. So now, if we have shown quadruples about our two threads E1 and E2, if the system is not interrupted by a crash, then we get the standard picture we saw before, where at the join point we'll know Q1 star Q2 holds. But if we are interrupted by a crash, well, at the moment the crash happens, from the crash conditions that we've proven about E1 and E2, we know that the resources of E1 satisfy T1 and the resources of E2 satisfy T2. So at the moment that the crash happens, or you could think like just before the crash takes effect, we'll know T1 star T2 holds. All right, so this is now enabled to describe an intermediate state of the system that could be exposed by a crash. However, we need one more extra concept here to really make this work, because we have to account for the fact that crashes modify state, right? So memory, for instance, is wiped out, but disk blocks might be unchanged. If you have different types of program state, like you're reasoning about files directly, there's different effects that crashes can cause to your program state. Okay, so we need a way to reflect in the logic that program resources are potentially perturbed by the crash itself. All right, so Perennial models this with a modality, which I'll write as this filled in diamond here, and we call this the post-crash modality. So the way to read this is we'll say P entails post-crash Q if resources that satisfy P will, after a crash and restart, satisfy Q. All right, so for example, on the left here, an in-memory points to fact. Well, after a crash, memory gets wiped, so that just entails post-crash of true. It's basically useless. Whereas for our purposes, disk blocks will be stable, and so after a crash, they just continue to have the same contents. All right, so once we have this idea, what we can do is actually fill in our concurrent composition thing by making the crash condition be diamond T1 and diamond T2. Okay, so now what we'll know is after the system restarts from the crash, we'll know T1 describes the things that E1 previously held, and T2 describes the things that E2 previously held. So we know that the recovery procedure will be able to start with T1 star T2. Okay, so taking stock, what we've seen so far is a way to describe the system in normal interleavings with no interruption. And also, we have a way to describe the status of the system after a crash occurs, but we haven't yet seen a mechanism to handle the fact that crashes can occur repeatedly, in particular, re-interrupt our recovery procedure. So the way we're going to address that is, well, we'll start by thinking about how is it, after all, that system developers manage to get recovery code to work. And the idea is that they design their recovery procedures to be idempotent. What I mean by that is they make it so that rerunning the recovery procedure an arbitrary number of times is sort of fine to do and always brings you back to the same state. Okay. And in particular, if you're interrupted in the middle, then it's safe to just keep rerunning it. All right. So we can formalize this idea of idempotence through the use of crash conditions. In particular, if we make the precondition of our recovery procedure be some assertion T, and then we require that the crash condition is also T under the post-crash modality, then we get something like the diagram on the right here, where we'll know that we can restart and assume that T still holds when we need to rerun the recovery procedure after repeated crashes. All right, so this is what enables us to consider arbitrary numbers of crashes, but we just prove one quadruple once and for all about the recovery procedure. Okay, so let's look at an example of that in the case of our replicated disk recovery. What we're going to assume as a precondition is a big separating conjunction iterated over each address on our disks. And for each address, what we're going to say is that there's some block contents stored for that address on the two disks. And what we'll stipulate is that if those don't match, then it must be the case that the dirty bit for the address is marked. Okay, so this is sufficient to ensure that after the recovery procedure runs, we'll make sure that we get every address that could potentially be out of sync, right? Because if they don't match, well, it'll have to have been marked and so on. And this is idempotent because we're conservatively saying, if they don't match, it definitely has to be marked. So if we partially do some recovery, like we get halfway through the addresses and then a crash happens again, that's okay, because we're not saying only the out of sync addresses are marked as dirty. We're just saying if they don't match, then they have to be marked. Okay, so to put it all together, if we want to reason about a system that's running two threads, EA and EB, and has some recovery procedure, ER, then we have to prove two sets of facts. First, we have to prove a quadruple about EA, about each of the threads. Okay, and then we have to prove a quadruple about the recovery procedure, where its precondition should be the separating conjunctions of the post-crash facts for the crash conditions of the threads. And the recovery procedure has to be idempotent, okay, so that it can tolerate repeated crashes. All right, so then the soundness theorem that we've proved for Perennial shows that this will cover all possible executions. So if we take one of the traces that I was illustrating before, right, the first bit before the initial crash, highlighted in orange, is covered by the first line. And then the safety, so to speak, of the recovery code is handled by the purple line. And we inductively prove that an arbitrary number of crashes is covered. All right, and now the caveat, I'm showing the version of what kind of the soundness theorem is obliging you to do for something with two threads and a single recovery procedure here. But the real full-fledged, full-strength version of the theorem covers an arbitrary number of threads. It handles dynamic forking of threads, and also the recovery procedure itself is allowed to be multi-threaded. But it's kind of all a natural extension of this intuitive idea I've given so far. Okay, so that's the key way that we adapt the underlying idea of concurrent composition from separation logic. I want to talk about some of the other concepts that I said have natural crash analogs. And the first involves the idea of doing ownership transfer in the presence of crashes. So in the diagram we've seen so far for reasoning about concurrent composition, our two threads were depicted as accessing disjoint pieces of state. Okay, so we split up our initial state into separate pieces, and then they were each enabled to access the things they owned, and we said that this was justified because they wouldn't be interfering with each other. All right, but in real concurrent code, threads need to share resources. Okay, they, for pure parallel processing things, you can consider things in isolation, but for serious concurrent storage systems, like I mentioned, you need to be able to share. All right, so the way that's typically handled in concurrent separation logic is that we model synchronization primitives as transferring resources between threads. So if we think about a lock, the standard concurrent separation logic specification for a lock will associate a lock invariant with the lock. So that's an assertion S here, which should hold whenever the lock is free. And now the idea is that when a thread acquires a lock, it gets ownership of the resources described by the lock invariant. So we augment the resources we initially had P with S. So now the thread has access to P star S while it executes some critical section E. At the conclusion of the critical section, it needs to reestablish that the lock invariant S holds. And when it calls release, it has to give up ownership of the lock invariant resources S and return them back. Okay, so that some future thread that acquires the lock may itself get to take ownership of S. Now, this standard specification for locks is insufficient if we have to handle crashes, especially if the lock protects durable resources like disk blocks. Okay, because the issue is if a thread now crashes in the middle of its critical section, well, the standard lock specification just says that the lock invariant has to hold at the beginning and end of the critical section. It doesn't say anything about S in the middle of execution of the critical section. So we're kind of in a similar problem of not being able to describe the intermediate state of these resources. So the way we address that in Perennial is, well, we add a new invariant associated with the lock, which we call a crash invariant. So the idea here is that the crash invariant is a weaker assertion, SC, which should always be implied by the lock invariant S. Now, when a thread acquires the lock, it gets ownership of the resources S, but its crash condition is also augmented with the crash invariant SC. All right, so you can think of that as saying you get ownership of S, but now you must promise to maintain the crash invariant for as long as you hold the lock. All right, so in particular, when the critical section ends, if it's not interrupted by a crash, and we call release, the thread will relinquish ownership of S, but it also discharges the crash condition, the crash invariant from its crash condition. So it's no longer in charge of maintaining SC. What this does is it buys us that if we have a crash in the middle of E now, well, from the thread's own crash condition, we know that R star SC has to hold. So we know that we can describe something about the status of the resources protected by the lock. Of course, if a crash happens while the lock is free, no one's holding it. Well, then, as I said, the lock invariant S should imply the crash invariant. So we'll also know that SC holds in that case too. Okay, so the key idea is that basically the crash invariant is going to hold at all times, and therefore, in particular, at the moment of a crash. Let's look at an example here. So for our replicated disk library, the lock invariant that we're going to associate with each address's lock is going to say something strong. Okay, it's going to say that the two addresses across the disk have to be synchronized. So they have some common block contents B. The crash invariant is a weaker assertion, which is implied by the lock invariant. It merely says that, well, what we were saying should hold for each address, that if the block contents associated with those two addresses don't match, then we must have marked the dirty bit. Okay, so the thread that acquires the lock as part of its write will be able to ensure this crash invariant holds at each step because of the fact that we put the mark dirty on line 3 before the first write to the disk. Okay, so the next concept I want to talk about is the famous framing principle. So I motivated separating conjunction in terms of what it buys you for reasoning about concurrent composition. But even before concurrent separation logic, there was, of course, plain separation logic, where there, one of the key things that separation logic bought for you was this frame rule, which enabled us to do local reasoning about the pieces of state modified by some program expression E. So the famous frame rule here says that if you prove a triple about some expression E, where you only need the resources described by P in the precondition, and you conclude with some postcondition Q, then you can derive automatically a triple in which you augment both the pre and post condition with separating conjunction of S. All right, and the underlying intuition here is that by the very fact that we have the separating conjunction here, S is disjoint from the resources P that E accesses for its execution. So we know that E doesn't affect S as it executes. So that's why we can just deduce that S must hold in the post condition for free here. Okay, so we've worked out a natural generalization of this to crash framing, all right, which looks very familiar, right? So basically now, instead of augmenting just the pre and post condition with S, we also augment the crash condition with S, right? So the reason that this rule is sound is kind of the same underlying intuition for why framing works in the first place, right? We know that E does not need to access or affect the resources described by S, so we can be sure that at each intermediate execution point of E, the resources in S still hold. Okay, so that's why the crash condition can be R star S. What's nice about this is kind of in the limit, if you have code that's only accessing stuff that's in memory, you can basically frame out all durable states and get down to a situation where your crash condition is just true. All right. And then we have a rule that says, well, a quadruple in which your crash condition is true is equivalent to a plain old Hoare triple, right? So if your crash condition is true, that's not really any extra obligation over what a normal Hoare triple obligates you to. So what this means is that when we're reasoning about code that's purely in memory, we don't have to worry about crashes at all, which is how it should be. Okay, so this is very nice because even though we're thinking about storage systems, even your file system has huge chunks of code that are just about in-memory data structures, manipulating hash maps and so on for caching. Okay, so this really eases the proof burden for those chunks of code. And it also lets us reuse sort of generic libraries that we've proven about in-memory code in the context of a crash-safe system. All right, the last concept that's been of importance in reasoning about concurrency that I want to talk about in the crash safety setting is the idea of linearizability and atomicity. Okay, so many concurrent separation logics have principles that enable you to establish that an operation behaves as if it were atomic, that is, as if it took effect in some single step in time. There are a number of motivations for why you want to prove such a thing. First, it's in its own right kind of an interesting correctness condition. But also, a number of these logics also allow you to, if you've established that, you can use special reasoning principles when thinking about code that has this property. In particular, this is an important component of kind of doing data abstraction and refinement reasoning for concurrent systems. So, for example, a replicated disk library internally has two disks, but ideally one would like to prove a specification for it that abstracts over that and just presents the same interface as a single disk that one would write to atomically. Okay, so a key component in establishing such a refinement is to be able to prove that the behavior of our replicated disk is atomic with respect to concurrent operations. But we also need to account for what it means to do this kind of atomicity reasoning if we have interruption by crashes and the need to do recovery. So in order to talk about some of those challenges, what I want to do is explain, I won't be able to give the full proof rules for this, but I'll just talk about how we adapt a challenge that arises in standard CSL reasoning to this context. And so normally these logical atomicity proofs, they center around identifying what's called a linearization point. So the idea behind linearization points and linearizability is you have some data structure that exposes operations, say F and G, and you want to prove that these operations behave in an atomic fashion. What you have to do is identify the so-called linearization point at which we can think of the operation as atomically taking effect. So here I'm indicating those points with red dots. So the idea is you have to show in the duration of the call of, say, of F or G, you have to pick out the point at which the operation has done its atomic effect. Now, if we have a crash, then we're not just interested in when an operation may take effect from the perspective of other threads. We're also interested in when an operation is durable and will persist or still have taken effect even after a crash occurs. Okay, so instead of a plain linearization point, what we do is we talk about commit points, the moment when the operation is durable and will survive a crash. So here, a crash has interrupted three operations. The one on the far left and the far right, we'll think of those as still taking effect, still registering their effects even after the crash, because their commit point occurred prior to the interruption by the crash. On the other hand, the middle operation was interrupted before the commit point occurred, so we'll think of that as not taking effect at all. Okay, so concretely, in the case of our write procedure, a classical linearization point could be anywhere in between when we lock and unlock. Right? And that's because, from the perspective of other threads, they can't tell until we've unlocked. So we can think of the operation as logically taking effect at any point in that range. On the other hand, the commit point is constrained to be precisely when we carry out the write to the first disk. Because it's at that point and no earlier that if a crash were to occur, the write will take effect. Because as we saw, recovery is going to copy over our write to disk 1 onto disk 2. So what we've shown in Perennial is that if we take some of the mechanisms that have been developed for reasoning about linearization and logical atomicity, we can adapt them to handle this idea of durable commits. Okay, so there have been a number of proposals for doing this logical atomicity reasoning in the literature. We adapted an approach that was proposed in the HOCAP program logic and was prefigured by a work of Jakob and Pieces. And the details I can't get into, unfortunately, although I'd be happy to chat about them in Q&A or offline. But the key idea is that because we have this crash condition that we've augmented our specifications with, we're able to encode the constraints that arise for marking that the commit point has to happen at that narrower window I just specified. Okay, so I've talked a bit about many of the principles that occur in Perennial. I'm going to switch gears now and talk about how we've applied Perennial to verify a concurrent transaction system. So in the course of developing the program logic, we were also verifying this system. So it's kind of like we were building the airplane as we were flying it. For me, this was a rewarding experience because I was working with a bunch of really great systems hackers on this. And so we were able to, come up with new reasoning principles, apply them to improve our ability to verify the system. That would again trigger new ideas for, okay, how can we codify these informal reasoning techniques that developers have and so on. So it was this fun virtuous cycle. And the system that we verified, well, okay, and rather than describing the details of the system in this talk, I actually, though, want to focus on using it as a kind of evaluation of the reasoning principles in Perennial. So I'm going to explore three questions here. First, do these reasoning principles, do these Hoare quadruples make proof effort easier? Second, do they actually buy you modular development? And also, are they expressive enough to handle the kinds of crash safety patterns that occur in realistic systems? Okay, and the artifact that we verified here is an NFS server called Daisy NFS. So this is a network file system server. It's decomposed into two parts. Um, the bottom is a transaction system that we verified with Perennial. This provides atomic transactions to the file system logic implementation, which is on top, implemented in and verified in Daphne, which this kind of makes up the capstone work of Tage, one of my co-authors on this, who is also on the job market, I feel obliged to mention. So I'm going to talk today about the underpinning here, because that's the part that was verified with Perennial. But the overall system is pretty cool. And if you're curious about the details, find Tage. I think he's in the workshop. So yeah, make sure to follow up with him. Okay, so on the question of proof effort, what I've done here is extracted the lines of code and lines of proof for GoTxn, the transaction system we've verified. And I'm comparing it here to two other verified systems that are kind of in the storage system space. So FSCQ was an earlier sequential crash safe file system, and AtomFS is a more recent concurrent in-memory file system, so it doesn't have to think about crash safety. Okay, and the reason I'm comparing against these two is that they're both verified in Coq using frameworks for doing either concurrency or crash safety reasoning. And as always, when we look at these ratios of lines of proof, we all know that one must take those kind of things with a grain of salt. But the point I want to make here is that we're kind of in the same order of magnitude between these two systems, even though we have to handle both concurrency and crash safety. Okay, so what I want to make the point here is just that the combination of these features, we have them under control to some extent. They're not interacting in a very poor way because of the principles we've come up with. So those 30,000 lines of proof for this system, that's kind of actually terrifying when we tallied it up after the fact to realize that that's what we'd done. But what made all that manageable is that we were able to carry out the development in a modular way. Okay, so as evidence for that, what I've got here is a list of all components, uh, both the logic itself and the different layers making up the implementation. And we were able to carry out the verification of each of these layers independently. So on the right here, I've got all of my co-authors on this work assigned a letter to protect the innocent here. And what I've done is I filled in a circle to indicate who worked on what in this whole verification here. And now you can see why I've anonymized it. Okay, so what you can draw from this is that a couple things. Various layers here were worked on by different people, although there were some that were particularly tricky and were cross-cutting in some sense. And also, the other thing to look at here is that some of the co-authors here were purely, so to speak, consumers of the logic. Okay, so they didn't have to understand the internal guts of the soundness proof and so on. We were able to set up pretty good abstraction boundaries there, and they were able to productively use the rules of the logic to carry out this large scale system verification. Okay, and on a more humorous note, one thing I'm happy about here is that we kind of spanned the whole spectrum of academic experience. We had everything from an undergrad who did a great fifth year master's program thesis on this work, uh, a PhD student, a postdoc, junior faculty member, tenured faculty member, and an endowed chair, and everyone did some hacking on here. So that was a lot of fun. Okay, and the last question here is, does this system actually carry out realistic, is it a realistic artifact? Okay, and so I want to make the argument that yes, it is. So Daisy NFS is a real mountable NFS server. You can mount it with the Linux NFS client and interact with it and do all sorts of standard file system operations. And its performance compares favorably with the Linux NFS server. Okay, so here I'm showing a variety of benchmarks that we did. Small file is a metadata heavy benchmark where you create a bunch of files and delete them and so on. Large file is about measuring sort of raw write throughput, where you're writing out huge chunks to a large file. And then app is an application benchmark, where we clone a small kernel used in the operating systems course at MIT, and we clone we run make on it. So that's running GCC and doing all sorts of various file system operations. Okay, and what you can see here is that DayZ NFS's performance relative to Linux is comparable. In fact, we exceed Linux on a few benchmarks, though. This, I should say, this is Linux running ext4 under the hood for the NFS server. Again, the fact that we do better on some benchmarks, don't take that too seriously. We're not trying to claim that this is better than ext4, but we're just making the argument that it's comparable performance. All right, and that's single core performance. We can also look at scalability for multi-threaded execution to say that we really did reason about serious concurrency here. And to that end, right, so here I'm showing the small file benchmark as we scale up the number of clients accessing the server. And, it's not perfect scalability, but for a modest number of clients, we are getting improvements, and it follows a similar curve structure to Linux. Again, scaling a little bit higher, but don't take that too seriously. Okay, so that's what I want to say about this artifact. I should mention some related work in this space of concurrency and crash safety reasoning. I've already mentioned the purely crash reasoning and the purely concurrency reasoning, but there's also been stuff that's looked at this hybrid. So fault-tolerant Csl is a logic that was developed by Philippa Gardner's group a couple of years back, which is a similar marriage of crash safety reasoning into separation logic. That was a pencil and paper logic, so no mechanization. And it didn't have this idea we had developed about crash-aware lock specifications, because they used kind of atomic blocks to do synchronization. There's also the very impressive FlashX verified flash file system work. So in that work, they originally started with a sequential file system that they proved crash safety of. And then in the past year or two, they've layered on concurrency reasoning onto that. That was verified in the KIV theorem prover, and it uses a mix, I would say, of methodologies for doing the verification. So it uses a variant of Lipton's movers to do concurrency reasoning, as well as some rely guarantee reasoning, and they rely on refinements up the stack that capture crashes. So it's a little bit hard to directly compare the approaches since they're so different. I mean, I don't even think people have a good comparison of, just for concurrency, how movers compare so well with separation logic. So when you throw in crashes into the mix, it's even harder to do a good comparison, but that work is very impressive as well. Okay, so that's all I had to say. So thank you so much for your time, and I'll be happy to take questions about the system.
Thanks, Joe. We have a couple of questions online. I don't know if you can see them. Otherwise, I can read them out loud.
I can see them. Am I supposed to select them, or are you supposed to select them? And like, there's a thing where it shows up for everyone, I think.
I would say
yes. So we can go in the order that they were asked. So starting from Herman's question.
Okay, so how hard would it be to apply your approach if writing to the disk is not atomic? Upon a power failure, there could be a partial write that corrupts a 4K block, giving an unknown state. Yeah, so there's two facets of the disk model here. So I think, okay, so two things here. I mean, you could model the idea that a write even to a 4K block is not atomic, and you could adjust our crash modality to capture that fact. At the end of the day, you do need to assume some at least discrete chunk will survive, maybe 512 sector. So what we could say is that under our post-crash modality, some prefix of the 4 kilobyte write took effect. The other thing here is I've been presenting a synchronous disk model, where as soon as you do a write, it's durably on disk, but real disks are not synchronous. You have to issue barriers to really flush things, and we've worked out a way to handle that in the presence of concurrency and some unpublished work. So yeah, we can account for that. It's it does add some challenges, but yeah, it can be done.
Okay, thanks. There's also one question by Benjamin that is the most popular question. Some upvotes.
So
why is the performance curve? Yeah.
I don't have a great answer to that question. You know, tuning NFS servers is a bit of an art. We did our best to try to tune the Linux server. The way that it works is it has a bunch of dedicated kernel threads that are supposed to respond to things, and we tried to tune the number that there should be. It's possible that our implementation, which uses like Go threads to handle incoming responses, is better equipped to, if there's more requests than threads, it adjusts to that more dynamically. But I don't have a great answer to that, unfortunately.
Okay, there's also a technical question by Herman asking about the rule for framing and the crash condition that is on all three of the quadruple, or all three parts of the quadruple.
Right. So the rule for framing shares the same S on both the crash assertion and the regular pre-post. Is there side condition, some notion of purity? Otherwise, can I move crash predicates to regular pre-post and nest them in other invariants? Okay, so there's no side condition there. You can weaken S if you wanted to after the fact. So there's a weakening rule where you can say, sort of like standard rule of consequence. The maybe what this is getting at is a common point of confusion in our terminology, which is the crash condition is not what the state of the assertion will be after memory gets wiped. It's kind of, sometimes TH likes to call these halt conditions. So it's what the state of the resources are, right before the crash takes effect. So when you get interrupted, but you haven't really killed memory yet. Okay, so that's why it makes sense to just push S directly into the crash condition. We capture those other effects through our crash modality. So to go under that diamond, S may have to get weakened. You may have to discard memory facts and so on. But yeah, hopefully that answers the question.
I have a semi-technical questions.
Mm-hmm.
So I wonder about, have you had to deal with non-fixed linearization points? I wonder how that interacts with crash safety.
Yeah, so we do handle non-fixed linearization points. So in particular, we can handle like helping patterns where another thread carries out linearization point on your behalf. We're able to use similar techniques that you see for handling helping and non-fixed linearization points in the separation logic literature. Actually, we're forced to use those techniques because the problem becomes even worse, especially when you have asynchronous disks, like I mentioned before. The non-fixed points show up a lot more. And so we're able to use kind of some variant of techniques for prophecy reasoning to handle those. And we have some unpublished work that we're excited about that handles that. Hopefully that, since you're in person, I can ask, did that answer your question?
Yeah, thank you.
Okay. What are you going to verify next? So the immediate project we're working on that kind of builds on this is there's been some fantastic work using separation logic to reason about distributed systems, some of which Amina's worked on, also Ilya Sergey and James GoTxn have worked on. What we want to do is handle the fact that in distributed systems, you often want to allow, if a node fails, it should be able to recover and try to rejoin the system. And so we think we can use these underlying ideas in Perennial to be able to handle that recovery of nodes and rejoining. The added wrinkle there is that whereas in a crash here, every thread stops, right? In a distributed system, if one node crashes, then threads on that node stop, but the others keep going. So we have to adjust some principles there, but we have a project with that on that, and we have some great students working on that right now. Oh, I guess that I should say more specifically. Well, we want to reason about like a fault-tolerant, recoverable kind of consensus system in that setting.
All right. Is there any other question maybe from the people in the room?
Not that I can see. No questions.
All right, then let's thank Joe again.
Thank you all.
Maybe we can continue to the next talk. Thanks, Joe.
Thanks.